Welcome everyone to the 5th lecture in the Advanced Topics QIT course. In this lecture, we will really spend, I guess, all of our time speaking about resource theories, a little bit of time speaking about a resource theory as just a formal mathematical construct, and then quite a bit of time talking about noisy classical operations, delving into detail as to what sort of resource theory it is, what are the criterion and the monotones and the resources that we get out of it. The reason we spend a lot of time doing this is because eventually we will do the simple proof that, in fact, noisy quantum operations can be reduced to noisy classical operations in terms of the constraints of whether you can or cannot perform a transformation on a state. And after dealing with this, we will go to thermal operations, which really bring us back into thermodynamics with Hamiltonians and temperatures. And in the resource theory of thermal operations, we will consider different variants of it, considering the single shot case of converting rho to sigma, considering the rates of conversion case, where you want to convert a certain number of copies of rho to a certain number of copies of sigma, where this m is equal to n times r, where r is the rate of convergence. So it's sort of the number of copies of rho you require per copy of sigma that you create. Oh, sorry, I wrote rho on both sides. That should be sigma. And then finally, we have the case of catalysis, where you want to convert rho tensored some other state, let's say eta, into sigma tensored eta. And of course, as the name suggests, you leave the catalyst eta the same. And this allows you to do something more. And in each of these different resource theories, we get different constraints. But one of the main things that we see in all of them is that the comparison, the distance between our initial state and the thermal state matters. And this distance can be written in terms of the free energy. So we will end with sort of a comment that the free energy is in fact the most significant monotone that exists in quantum thermodynamics. All right. So let's begin. And we're going to begin with, I'm sorry, stuck. Yeah. Resource theories, which is a bit of a repetition of what we mentioned in the last lecture. So what is a resource theory? A resource theory is defined by two things. You have a state space. So you have rho, sigma, eta, etc., belonging to some state space. I'm just going to call it S for now. And then you have allowed transformations. Maps that act from S back into the state S. So you have M acting on rho, which gives you rho prime. And once you start with these two ingredients, a state space and a set of allowed transformations, what this allows you to do is to take every state rho and then consider all of the states it can go to. And of course, then you can go from these states to other states via the allowed transformations, and you end up with a graph that gives you the set of all allowed transformations. So for example, a very simple artificial graph that I can draw is, consider a state that I label A, that can be taken both to B and to C, and these can be converted to each other. B in turn can be converted to D, C can be converted to E, and that's it. Okay, so this is a graph. Now, this is not a complete graph, because what I also am allowed to do is, if B is equal to M1A and D is equal to M2B, then that implies that D is equal to the composition M2 on M1 of A. So this automatically implies that I can also draw this arrow here. I can also draw this arrow here. I can also draw this arrow here. And I can also draw that arrow there. Yes, so this is another way of saying that in this graph, this ordering between all of the elements, we end up with a pre-order and the properties of a pre-order are the following. One is it is reflexive in the sense that A can always go to A, and the reason is that doing nothing is always allowed. So this is always part of the allowed transformations. And the second is that it's transitive, because if A goes to B and B goes to C, let me use the graph, so B goes to D, then this implies that A can go to D, and this is because we can always compose transformations together. Okay, sorry, apologize. A very simple example of, sorry, there's a question.
No question. Is this like two properties the definition of pre-order, or does it mean something else?
No, these, if I'm not mistaken, these are the only two that define a pre-order. Yes, indeed. If you add anti-symmetry, which is that if A can go to B and B can go to A, then A and B must be exactly the same, then you get a partial order, which is even stronger. But a resource theory does not give you that. A resource theory gives you a pre-order, because, for example, here in this particular graph, you have B and C that can both go to each other, but they need not be equal.
Okay, thank you.
So one example, very simple, is the vectors under doubly stochastic matrices. So this here is our state space. So it's a space of real dimensional vectors. So it's V belonging to R plus D, and doubly stochastic matrices are the allowed transformations. Yeah. So for instance, I know that the state 1, 0 can be taken into the states 2/3, 1/3, as also 1/3, 2/3, and this in turn, of course, can be taken to the state. These both can be taken to the state 1/2, 1/2, and the directionality, and this as well, 2/3, 1/3, and 1/3, 2/3 can be taken into each other by permutations, which are doubly stochastic matrices. And another way of saying this is that majorization, which, as we remember, was both a necessary and a sufficient condition for a vector to be taken to another by doubly stochastic transformations, is a pre-order. Okay, so right, so this is now a general definition of a resource theory, and what we get here, this is a necessary and sufficient condition or criterion. But we didn't have this always in a resource theory. So in a resource theory, we look for functions f of rho comma sigma, and if that have the following properties. So if it is the case that rho going to sigma implies that f of rho comma sigma is greater or equal to 0, this defines a necessary criterion. And if f of rho comma sigma is greater or equal to 0 implies that rho can be transformed to sigma, that implies that it's a sufficient criterion. Okay, so these are useful criterions to find out, like majorization, but even more useful is if we have f of rho comma sigma is equal to actually a function on rho minus the same function on sigma. So you have a function that depends only on one of the states. Well, it's a function defined from the state space to the set of real numbers. If you have that f is given by such a thing, in the case that f is necessary, if it's a necessary criterion, we call it a monotone. Right. So what does this mean? It means that a monotone is something for which, again, if rho can go to sigma, it must imply that g of rho must be greater or equal to g of sigma. So a monotone is somehow the value of a state. If I am allowed to go from one state to the other, then a monotone is some function that must always be decreasing or staying the same. And in fact, if I have, we can see immediately that if rho can go to sigma and vice versa, then it must imply that g of rho must be equal to g of sigma, because if not, one of them would not be possible. Okay. Now, an example of these in the case of vectors under doubly stochastic transformations, an example is all Schur-convex functions. Because remember, a function was Schur-convex if and only if. So if, let's write it on a new line. This was the statement that if x majorizes y, which is the same as saying that y is equal to some doubly stochastic transformation of x, that it implies that f of x must be greater or equal to f of y. So one example is the negative of the entropy. So f of x is equal to the sum over I, xi log of xi. The reason it's a negative for the entropy is because, of course, the entropy itself is Schur concave. It goes the opposite way. But any Schur concave function, you can, just to keep the convention that majorization means greater or equal to for monotones, you can simply multiply by -1 and you get a Schur-convex function. Right. Okay, are there any questions so far? Nope. All right. Let's continue. So, right. Now, in the graph that I drew up here, this was a very artificial graph. We had the case that there was a single state, A, that could go to every other state. But we had the case that there were two, I would call them dead end states of this resource theory, which are states where you cannot, you essentially from there, it's not the case that you can go somewhere and not come back. So these are the dead end states D and E. Now this is just an example, an artificial example. The number of extremal states on either end really depends on the resource theory that you pick. So for example, in the case of majorization, we have that pure states are extremal. So if we have any state of the form 1, 0, ... and this is of course D times. So we fix the dimension D when we are talking about doubly stochastic matrices. Then all of these are extremal in the sense that they can be taken to every other state, including amongst themselves. But there's only one state that's a dead end, which is the maximally mixed state, 1 over D, 1 over D, 1 over D, so on. Okay. Now, this takes us to the notion of free states. So There are two definitions of free states. It turns out that most of the theories that we will deal with actually have the stronger definition. And the weaker one, so the weaker definition is the following. Given a free state, let's call this eta, and any other state rho, there exists M such that M of rho is equal to eta. So given any state and a free state, you're always guaranteed that you can go from that state to the free state. So the free states are somehow therefore defined as those that you can always get to no matter what your starting point in the resource theory was. The stronger definition of it is the following. Now, in the weaker definition, the transformation M that we choose in order to get from rho to eta can very much depend on what that initial state rho was. So given different initial states, rho 1 and rho 2, it might be that you have different operations that would take you to eta. But the stronger definition of a free state is that given free eta, there exists an M such that M rho is equal to eta for all rho. So this is a stronger condition. This says that no matter what your initial state is, there is some transformation that will just take you to this free state. It's just independent of your initial state. It will get you to the free state of the resource theory. Now, an example for this, and this is where we go now to noisy operations. So remember, the quantum version of noisy operations was you take rho, you tensor it with the maximally mixed state, let's say A on dA, you do any unitary on it, and then you trace over some part of the Hilbert space. And the classical version of it was very similar. You would have to have, you take rho, sorry, in the classical case, you have vectors. So you take an X input, you tensor it with, I'm going to call it MA, and M for reference will always refer to the uniform distribution. Take rho X times MA, you do some permutation on this, and then you trace out A from this. Oh, well, A bar, because it doesn't have to be the same as A. So this is the classical version of noisy operations. Now, the first thing, the immediate thing that we can conclude for the case of noisy operations is that every maximally mixed distribution is a free state. So every, in this case, it's identity over A, or identity over anything. So identity over input, let's say, the input. And in this case, it's every M input is free. And the reason is because if I'm asked to make a particular free state, there's a very simple transformation that gives me that free state. No matter what initial state I have, I add the free state that I'm looking to get, and then I just trace away my initial state. So regardless of the initial state, I'm always going to end up with the maximally mixed distribution that I added. And this is a general property of any resource theory that has, that is constructed in this form, where I can add free or add particular states that are allowed, and then make a unitary, and I'm allowed to trace off whatever part of the global state that I wish. So in some sense, even though a typical resource theory starts with allowed operations from which we derive what free states are, here somehow the construction of the resource theory already provides us with what the set of free states are. And these free states satisfy the stronger definition that we have just discussed, because we have transformations that will take us to any free state we like, independent of the initial state that we begin with. All right. Any questions? Nope. Okay, so now let's spend a little bit of time revisiting rather the resource theory of doubly stochastic matrices. So in the case that we have, so now we're going to focus now on noisy classical operations. And the interesting thing to note is that in noisy classical operations in general, the dimension of my input state and the dimension of the output state does not have to be the same, because I can always trace over a different part of the space as I started off with. But let's just briefly revisit what happens in case the dimensions are the same. So if dimensions are the same, then what we have is that there's an equivalence between, so noisy classical operations are exactly the same as uniform preserving operations. And this is something that you'll have done in the tutorial, if I'm not mistaken. Noisy classical operations the same as uniform preserving operations, which are the same as mixtures of permutations. And these mixtures of permutations, as we discussed when we first discussed majorization, Birkhoff's theorem, a mixture of permutations is the same as a doubly stochastic transformations. So every one of these sets of operations that we can do are actually exactly the same. And we know already the solution to that resource theory. We have that majorization is both necessary and sufficient, and all Schur-convex functions are monotones. Okay, so now we look at the case of what happens when we have higher dimensions, or not higher dimensions, but different dimensions for the input and output states. And what we're going to look to do now in this case is, first of all, to find something, so something that generalizes majorization. So we want to generalize majorization because, remember, majorization requires you to compare vectors of the same length. You have to compare all of the partial sums up to any value k, but that requires the vectors to be of the same length. And the second is to generalize Schur-convex functions, because we need new monotones that will work for higher dimensions as well. Right, and one of the ways of seeing that our original Schur-convex functions don't actually work is take the negative at the entropy. So the negative of the entropy of a maximally mixed distribution or uniform distribution is log of the dimension, or actually it's negative of the entropy. So it's minus log of the dimension. But this is not the same for all free states, because we know that in the case of noisy classical operations, I can always go to any maximally mixed distribution. So if there is a monotone, all of those states in that set, in the set of free states, must have the same value for that monotone. So the negative of the entropy cannot be a monotone. You can also see this in the case of pure states. So the negative entropy of pure states is 0 for all pure states. But in fact, pure states of different dimensions are in fact not equivalent under the theory of noisy classical operations. And the reason is because the higher the dimension, the more valuable it is. A simple example is the following. Consider that I have the state x and y, and x is the vector 1, 0, 0, and y is the vector 1, 0. And I want to consider, can x be taken to y or backwards via non-noisy classical operations? Are they equivalent? Maybe all pure states would be equivalent. They're not, but let's see why this is not the case. And the way to see how to convert them is quite simple, which gives us a template for the general case. I see that they're not of the same dimension. However, what noisy classical operations allow me to do is allow me to add any mixed distribution I like and take away any mixed distribution I like, because I can simply trace out any part of the state that I would like to at the end of the operation. So what I can do is I can take x tensored m, and let's call this m2, which is the maximally mixed distribution of 2 dimensions. So this is half, half. And I get the following vector. I get half, half, 0, 0, 0, 0. It's a 6-dimensional state. And I can take y tensored m3, 1 over 3, 1 over 3, 1 over 3. And I get the state 1 over 3, 1 over 3, 1 over 3, 0, 0, 0. So I've already ordered them. And now we can definitely see that x tensored m2 majorizes y tensored m3, because these are now of the same dimension. So we know that we can go from x tensored m2 to y tensored m3, but this immediately implies that x can go via noisy transformation to y, because we can take x to x tensored m2, we can take x tensored m2 to y tensored m3, and we can take y tensored m3 back to y. Each one of these is a noisy transformation. All right. And so what this also shows us, so this shows us 2 things. So one of the things to comment on is that it shows that the entropy of the state is not even a good quantifier for pure states, because we see that pure states of higher dimension are more valuable than pure states of lower dimension, but the entropy of pure states are always 0. And the second thing it does is it tells us that we can always say x can go noisy to y if and only if x tensored, right in the same sentence, x tensored m dy can go to y tensored m dx. Because I can add uniform states on both sides of any dimension. So I will pick the dimensions in such a way that in the end, I get 2 vectors of the same dimension, which I can compare by the original theory of just majorization and doubly stochastic matrices. And once we have the criterion in that dimension, we know what the criterion on the original vectors are. So this reduces the whole problem of noisy classical operations to the same as the criterion for transforming vectors under doubly stochastic transformations of the same dimension. Okay. Any question? Okay. Right. And so in answer to our first question of, we had 2 things we wanted to do. We wanted to generalize majorization, and we wanted to generalize monotones. So the answer to the first question is that majorization can be generalized to Lorenz curves. So I apologize, last lecture I might have misspelled Lorenz with a T because I was thinking of the pronunciation. This Lorenz is not the physicist Lorenz. This Lorenz was an economist in the United States of America with German descent, hence the surname, who invented these curves when thinking about the notion of income inequality. Okay, so as a reminder, what is a Lorenz curve? It was the following. If we had a vector x in Rd, what we did is we split the unit interval into blocks of D. And then for each of those blocks, we wrote down the partial sum corresponding to that. So this was x1, this was x1 plus x2, and then you'd have x1 plus x2 plus x3, so on and so forth. And of course, at some point, they would add up to 1 because they're all property distributions. So you would get a curve that went something like that and eventually got to 1. So this was a Lorenz curve. And one of the things to mention is that the Lorenz curve is always of this form. It's always concave. And the reason is because x1 is greater than x2 is greater than x3. Remember, when we do the Lorenz curve, I forgot to say, we always order the elements of the vector first. This is what we're used to in majorization. First, we order the elements of the vector, and then we compare the partial sums. Okay, so now the Lorenz curve on its own is equivalent to majorization for the same dimension, because if we have this as a Lorenz curve, and if we have another Lorenz curve, let's say the Lorenz curve corresponding to the uniform distribution, which is just a straight line. So because all of the probabilities are the same, then you see that the Lorenz curve of the uniform distribution is below that of the other x that we chose. And this is a general statement between Lorenz curves and majorization. So for the same dimension, Lorenz curves and majorization are exactly the same, in the sense that if the Lorenz curve of x is greater than y, then that's the same as saying that x majorizes y. Okay, but the reason that Lorenz curves are more useful than majorization is because they generalize to higher dimensions. And the reason is that if we take x tensored maximally mixed distribution MA, then what does this give us? This gives us the following vector. We will get x1 divided by dA. D is the dimension of the uniform distribution that we appended. x1 by dA dot 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 dA times. And then another block of x2 by dA dot dot dot, and so on and so forth. So every element of the original vector x simply splits into dA elements of the same amount. And if the original vector has been ordered, so x1 greater than x2, x greater than x3, then the ordering doesn't change. You still have that x1 over dA will be the largest eigenvalue, just repeated dA times, x2 over dA repeated dA times, so on and so forth. But what this means is, consider what happens to the Lorenz curve now in this case. Let me draw it again. So my original Lorenz curve, and I'm only going to draw it for 2 points. So this was 1 over d, 2 over d, and you had this point, and then you had this point. So this was x1, and this was x1 plus x2. Now my new Lorenz curve, I'm going to have to split the unit interval, not by d times, but by d times dA times. So each of these intervals will also now get split into 1 over d times dA, 2 over d times dA, and so on and so forth, so that the unit interval is now split according to the dimension of the full state. So these points, original points that I drew before, they still are maintained, because you see that at the end of 1 over dA, 2 over dA, I eventually get to 1 dA over dA, which is 1. And so I get the 1 over d point that I had originally. And the points that we are going to plot here will all lie on this line, because they will be x1 times 1 over dA, x1 times 2 over dA, and so on and so forth, up to this will be x1 times dA over dA. So what you see is that appending a uniform distribution, all that it does is it keeps the same Lorenz curve. It simply divides every line segment in your original Lorenz curve by the dimension of the uniform distribution you've appended and adds points according to that. But the curve remains the same, which implies that if x tensored MA can be taken to y tensored MA bar, for whatever A and A bar are, we know that the Lorenz curve of this is the same. So L of this is equal to L of x. And we know that the Lorenz curve of this one is the same as L of y. So this must imply that L of x is greater or equal to L of y. So in summary, what we've done is we've said we can take x to y by a noisy classical operation if and only if we can add uniform distributions to make them the same dimension, and then do that via a normal doubly stochastic transformation. In that case, we know that majorization tells us everything we need to know, and majorization is the same as Lorenz curves for the same dimension. But because Lorenz curves are invariant under adding or taking away, tracing out uniform distributions, we might as well compare the Lorenz curve of the original vectors x and y, even though they're not of the same dimension. And so Lorenz curves are somehow the generalization of majorization to the case where the input and output dimension are not the same. Any questions so far? Okay, so the next thing we wanted to do is monotones. And what we're going to generalize monotones is relative or functions, relative Schur-convex functions. I might have gotten this nomenclature slightly wrong, but anyway, the meaning will become clear. So what is a relative Schur-convex function? Before we go there, well, for this, we need to have a bit of diversion. So remember that noisy classical operations are uniform preserving operations, in the sense that if you put in a uniform distribution into a noisy classical operation, you're going to get out a uniform distribution. In particular, if you have noisy classical operations of the same dimension, so the input and output are the same dimension, then you input the uniform distribution of that dimension, you get out exactly the same distribution. But you can generalize this to Q preserving operations. And what are Q preserving operations? Q preserving operations are linear operations that preserve some distribution, but it doesn't have to be the uniform distribution. It can be the distribution Q. So Q is now a distribution. So Q is the set Qi, I running from 1 to D. So Q belongs to R plus D. So you fix a special distribution Q, and you ask for all of the linear operations on the state on a vector that have the property that if you input Q into them, they will also give you Q on the as the output. And so then this is just nomenclature. You can consider that X majorizes, Q majorizes Y if and only if X can go to Y via Q preserving operation. So noisy classical operations are the same as uniform preserving operations. And so if we put Q to be the maximally mixed distribution, the uniform distribution, then we get back everything that we have. But if not, we can consider, well, Q preserving operations. And the reason that this is useful is the following. So one way of constructing a Schur-convex function is the following. We take a function g of, let's say g of, let's say x here, where x is, or g of xi, where g is convex. So this is just a function from the real numbers to the real numbers. And then we sum it over the elements of the vector. So if you take, this is the easiest way to construct a Schur-convex function. You simply take a normal convex function and you just sum up the values of that function for all elements of the vector. So the entropy, for instance, the example is g is equal to x log x. This gives us the neg entropy, which is a Schur-convex function. And the nice thing that we can do is, so we know that Schur-convex functions have the property that if x majorizes y, then the Schur-convex function of x is greater than that of y. But we can generalize to Schur-convex relative to Q. Let me get the nomenclature for this. Right, okay, I will clarify the nomenclature after we have a break. But the way to construct them is the following. So if I'm given a QI and a G, so I'm provided a Q and a G, this is a distribution, remember, and this is a function. Then I construct the following function. I say, let me take the sum over I QI times the function, but not on xi alone, but on the ratios xi over qi. So this is a new type of function, and this is guaranteed to be, well, to be Schur-convex relative to q. So I call this, I define this as gq of the vector x, or maybe let me call it, no, capital G, q relative to x, and it has the property that if x can be taken to y via q preserving operation, then that implies that gq of x must be greater or equal to gq of y. Okay, so an example is, so take g of p to be p log p. That's what gives us the usual entropy. What will we get here? We would get gq of x would be sum over I qi times, and now we do p log p, but with these. So we have xi over qi times log of xi over qi. So this is how the entropy has now been made into a new function that is relative to the distribution q, which in turn simplifies. So gq of x is equal to, so we cancel out the xi's and we get sum over I xi log xi over qi, which is equal to, there are many ways of writing this. I'm going to write this with, actually, let me write it as h in this case, the relative entropy of x with respect to q. So if those, I'm expecting that almost all, if not all of you, at least those who have done the QIT or QIP courses, will have seen the relative entropy turn up in some form or the other. And here you see we just get the relative entropy of x with respect to q. So to see why this works, take q to be the uniform distribution, which implies that qi is just 1 over d for all I. And then what we get is that the relative entropy of x given q is equal to sum over I xi log of xi minus log of 1 over d, which is so plus log of d, which is equal to log of d. Because remember, x is a property distribution. We're always dealing with distributions. Therefore, the sum over I xi of log of d just becomes log of d minus, and now I can write this as minus sum over I xi log xi. So it's log of d minus the entropy. And you see the log of d is the magic number here, because remember we said that free states under the usual entropy had under the usual sort of entropy function were just minus log d. But now we see that free states have the property that h of x given q is equal to log of d minus the entropy of the free state, and free states are maximally mixed states. So they're all, the entropy is always log d themselves, which is 0. And pure states have the relative entropy x versus q as log of d minus 0, because the entropy of pure states is 0, which is log of d, which immediately tells you that pure states of higher dimension are more valuable, because log of d is an increasing function in dimension. So you see that the pure states here are not all equivalent, unlike in the case of the same dimension. All right. Is there any questions so far? Nope. Okay. So a few comments here, or rather a very big comment. This, what we've just done, is actually a very powerful extension of the resource theory of noisy classical operations, because we've just said that if you make up any other linear resource theory that has the property that instead of preserving the uniform thing, you preserve Q. And one easy way of doing this is to replace the free states in our allowed transformations. Instead of putting them to be the uniform distribution, you put them to be distributions that are like Q. Then you will get another resource theory, and it is immediately straightforward to make up monotones for that resource theory. And in particular, this is very evocative of thermodynamics, because in thermodynamic resource theories, including thermal operations that we will discuss later in this lecture, the free state is tau, which is e to the minus beta h upon z, which is also the same as the preserved state. So it is a state that if you input that one, the only thing that you can get out is also a thermal state, which means that in those resource theories, the monotones that we will have will be relative to the thermal state. And in particular, one of the things that we can see is if we take a state rho, so, and we take tau, which is thermal, we can always find the quantum relative entropy between rho and tau. So this is called the Renyi divergence of rho versus tau, which is defined in a similar manner as the above, the relative entropy. And this turns out to be actually equal to beta times the free energy difference of rho minus that of tau. So relative entropy is one of the most powerful monotones that we will find in any resource theory. In particular, in thermodynamic resource theories, the relative entropy of any state with respect to the thermal state is a difference in free energies from that state to the thermal state, which tells you immediately why free energy is somehow the monotone that you hear the most in thermodynamics. One of the classical expressions of the laws, the second law of thermodynamics, is that in any thermodynamic scenario, the free energy of your resources must either stay the same or decrease, which is exactly something that you expect from a resource theory, given that free energy itself is a distance measure from your state to your thermal state, which is in turn the free state or the preserved state. Right. Okay. Are there any questions right now?
Yes,
Yeah.
a small question.
Yes.
Why did you call that last D D instead of H?
Oh, it's just this is just notation. I call it D because it's called the Renyi divergence rather than just the relative entropy. But it's defined the same way as the well, actually, the reason I started with H instead of D is just because I was thinking of D being doubly stochastic matrices. That's why I wrote H. But you can call it H or you can call it D. This is just nomenclature. Yeah.
Okay. Okay. Thank you.
Okay, if there are no other questions at the moment, then what I would suggest is that we take a break and we will return in 10 minutes from now. So at 16:45, we can. Okay, so let's continue. So just to get back to the question that was asked earlier, this is the appropriate answer. So the relative entropy, the quantum relative entropy, is defined via the whole density matrix as trace of this rho log rho minus rho log sigma, as long as it's well defined. You can have that it diverges sometimes if it is the case that rho and sigma, especially if sigma has a zero eigenvalue subspace that's not shared with rho, then it diverges the same way that the normal relative entropy diverges. If it is the case that rho and sigma have the same energy eigenbasis, then that can be simplified in that eigenbasis, and then you end up just taking the relative entropy of the vector of eigenvalues, which is typically written with H. So I guess this would be the correct answer to what's the difference between D and H. It's just that one is the more general version of the quantum relative entropy, and one is a classical relative entropy that are equal only under some circumstances. Okay, so, right. So everything we did so far was about noisy classical operations. And as I said, the reason that this is useful for us is because in the end, noisy quantum operations turn out to be the question of whether a state can be transformed by a noisy quantum operation turns out to be the same as that under classical operations. And so what we're going to show now is we're going to show that rho going to sigma under noisy quantum operation is exactly the same as lambda rho going to lambda sigma under noisy classical operation. And lambda is the vector of eigenvalues. Okay, and yes, so the way this goes is the following. So the fact that rho can go to sigma means that there is some operation, let's say the noisy quantum operation, epsilon acting on rho, that is equal to sigma. And now I simply expand what rho is in its own natural eigenbasis, in the eigenbasis in which it's diagonal. So this is summation over, let's call it J, lambda J of rho phi J, and this is equal to, and you have another eigenbasis here for sigma, psi k, psi k. So all I've done so far is just written out the density matrices in the basis in which they are diagonal. Now, because a noisy operation is a linear map, because it involves unitaries, involves tracing out, which are all linear operations, I can now reshuffle this and I get sum over J, lambda J rho, and the map simply acting on the state phi J, which is a projector, is the same thing here. And then what I do is I now sandwich this in a particular eigenstate of the final state sigma. So I sandwich both sides under this. And so what I get in the end is sum of J of this, psi k, the map acting on phi J, psi k is equal to, and on the other side, because I've chosen one of the eigenstates, it's going to pick out exactly that eigenstate, because the scalar product for any of the other with the other eigenstates is going to be 0. Remember that a density matrix, when we write it in the diagonal basis, the eigenstates are always orthonormal to each other. Okay, so this very much looks like a matrix equation, because what I'm getting here is that lambda k of sigma is equal to the sum over J of, and I'm going to call this d jk lambda J, oops, sorry. Let's not do that. Let's call it dkj lambda J of rho, and this dkj is defined by this. So we have a set of numbers, dkj, which forms a matrix for if you vary over k and j, and each of the elements of this matrix is defined via this expression here. Okay, and now all that it remains to show is that dkj is a doubly stochastic matrix. So what do? We note first of all that J runs from 1 to J is our input state, so the input, and K runs from 1 to the output. So then let's take the sum over J d of kj, which is the sum over J can be taken inside. I have the phi k epsilon, the map rather, acting on sum over J, phi j, acting on psi k. This, as we know, is just the identity operator on the input space. And now we want to know what happens if we put the identity operator in the input space through the map. Well, I can simply write this as psi k This is the identity operator input space. And what I'm going to do is I'm going to divide it by the input dimension, and I'm going to multiply by the input dimension outside. This is very simple to do. But this, by definition, is going to give us identity on the output space divided by the dimension of the output space, acting on psi k. And the reason is because we know it's the fact that a particular operation is a noisy quantum operation means that it is automatically a uniform preserving quantum operation. That goes from the definition, the same way as you proved it in the classical case. Here, the inclusion is a bit stricter. They're not equivalent. Noisy means definitely unital, but unital does not necessarily mean noisy, but we only need it in one direction now. So if we put in the maximally mixed distribution as the input, we get the maximally mixed distribution in the output. And this in turn is going to give us, well, now we have the scalar product of psi k with itself, which is 1. So we get d in by d out. And this, incidentally, is a generalization of what you need to get with doubly stochastic matrices when you sum over columns. So in a doubly stochastic matrix of the same dimension, the rows and the columns must sum up to 1. But in a doubly stochastic matrix that acts to take something to another state of a different dimension, we still must have that columns sum to 1, but rows sum to d in over d out. The reason is that this follows from the conservation of probability, and this is just from the dimension ratio. So this is a trivial thing that one can check. Okay, so the other sum to check is the sum over k of dkj, and you do this exactly the same manner, but here you do a little bit of a trick. Instead of taking the sum over a scalar product, I convert this into a trace. So I get trace of epsilon phi j, sum over k, k. I'm not sure anyone if you've seen this before, but this is because you can always take the scalar product and convert it into a trace by taking the bra and the initial and putting it at the end and doing it as a trace. You get exactly the same result. This is directly from linear algebra. And this is, of course, just trace of epsilon acting on phi j, because the other one is now the identity operator on the output space. Yes, and this is a map acting on a valid quantum state. So it's going to give us in the end a valid quantum state. And since it's a valid quantum state, the trace of that state is 1. So this we get is equal to 1. And so what we've shown, therefore, is that dkj is doubly stochastic, which implies that it's a noisy classical operation. And therefore, if rho goes to sigma via noisy quantum operation, then it implies that lambda rho can go to lambda sigma via noisy classical operation. Is there any question? Okay. And now we want to prove the opposite direction. So for the converse, so the converse direction, I'm not going to go into the entire proof, but the key to understand is that, so we start in the other way. So we have that lambda rho can be taken to lambda sigma by a noisy classical operation. And this implies that there is a dkj such that lambda, what is the equation that we have? Lambda k sigma. Yeah. Lambda k, the kth eigenvalue of sigma is sum over j dkj, the kth eigenvalue of the jth eigenvalue of rho. And all we need to do now is, so we have that the eigenvalues can be taken to the eigenvalues. All we need to do is to add the condition that the eigenvectors get taken to the eigenvectors. So we simply define a map like that. So we define it as, so with every dkj, what you do is, so this is a map acting on rho, is you take rho, you check whether it's in the state phi j. And if it is in that state phi j, you transform it into the state psi k with the coefficient that we already know works on the level of the eigenvalues. And then you sum this over all k and j. And this is now a map we've constructed from the noisy classical operations. We've constructed a quantum operation that will also have the same effect. And all that it remains to show is that this is a noisy quantum operation. Okay. So this is a proof that I'm not going to do in its entirety, but the way to do it is to understand that this dkj, because it's a doubly stochastic transformation, we can also write it as a mixture of permutations on a larger space. So remember that a doubly stochastic transformation, we can always write it in the form of, there is a permutation on X tensored MA that will take you to Y tensored MB. This is the same as saying that there is a doubly stochastic transformation that will take us from X to Y. And once we have the form of this permutation, all we have to do is we have to, for MA, we have to add the maximally mixed distribution, so 1 over dA, and we can write it as a quantum state, even though it's actually a classical state, a completely diagonal state. We can call this sum over I, mu I, and we append this 1 over dA bar, sum over J, for example. Well, I and J should be chosen to be separate so not to clash, but you can do this, mu J. And from that, we end up, and I'm not going to do this full steps here, you can leave it as a tutorial question. You get that this becomes the sum over K, J, let's say L and I. And instead of D, K, J, you have now an R, K, J, L, and I, which is a permutation. And instead of only rho, you have rho tensor identity over the input space. And these are now appended with the phi j and the nu I. Oh, I'm going to run out of space here. Phi j nu I, and which take you to the psi. Sorry, L I. Yes, no, this is good. Psi k and mu L. Same way here. Psi k and mu L. And after you get that, oops, still not enough space, you have to trace over A bar. And the reason that you can see that this is itself a noisy quantum operation is because what we have here, this transformation R, is effectively a change of basis. It's a matrix that has all zeros except for ones. There's a single one in every row and column. And every one of these transformations is one that takes a state phi j nu I to the state, to some state psi k mu L. So this is by construction a unitary operation because it simply tells you that it's a change of basis from Ji to KL. For every state in the original basis on the system and the ancilla, the uniform distribution that you add, you get a unique basis state of the final state of the system with tensored a state of the basis of the path that you're going to trace out. And so this in turn can be written as the trace over A of U rho tensored identity A over dA, U daggered. So all of this simply depends on the fact that in noisy quantum operations, it's really similar to noisy classical operations in the sense that the state that you add, which is the maximally mixed distribution, is effectively still a classical state. It's just a completely mixed state of all of the basis vectors of that Hilbert space. Is there any question? Nope. Okay, so with this, I'm going to conclude. So that's the end of noisy quantum operations, which, remember, all of the criteria and the monotones are the same as that of noisy classical operations, which is why we spent a good deal of time discussing the case of noisy classical operations. Okay, so I'm going to now go forward to thermal operations, which are the basis for a very large class of quantum thermodynamic resource theories. So what is a thermal operation? Thermal operation is the following. I have my state space now is the density matrices rho acting on the Hilbert space H of S. I also have a Hamiltonian H of S. I also have a thermal bath at temperature beta, which, as we discussed briefly in last lecture, it means that I always can pick for every Hamiltonian H of the bath, I will get the state for free. Tau is, let me call this gamma actually now. Gamma is equal to e to the minus beta H of bath by the appropriate partition function to make sure that the state is normalized. Right. And so what I'm allowed to do is I'm allowed to take, so rho can go to rho tensored with gamma. We do a unitary and a U dagger, and then you trace out the bath. So this is the system, this is on the bath, this is on the system and the bath, and you trace out the bath. So here you really remain in the same Hilbert space, unlike noisy quantum operations and noisy classical operations, where we considered possibly going to a space of a different dimension. Here we maintain that you stay in the same space even at the end of the operation. Okay, so, final very important condition is that USP must commute with the Hamiltonian of the system and bath. So HS tensor identity bath plus identity S tensor H bath must be equal to 0. So this is the notion of energy preserving Hamiltonians, energy preserving unitary operations in this case. Okay, so as with any resource theory, we ask a number of questions. So first we can ask, what are the free states? And these are thermal states, or the thermal state rather, tau is equal to e to the minus beta HS upon Z. The reason you see that this is a free state is because imagine we have a unitary acting on system and bath on the following state, tau tensored gamma, USP daggered. This is the same as USP acting on the state e to the minus beta on the total Hamiltonian H system bath upon Z, because if you take two thermal states at the same temperature and you take the tensor product, you get a thermal state also at the same temperature. Now, because this is energy preserving, it follows that it acts non-trivially only in degenerate subspaces. So from a while ago during this lecture, we discussed the fact that energy preserving unitary operations can always be written block diagonal in the basis of the Hamiltonian that is acting in, which means that for any non-degenerate eigenstates, so states with different energy eigenvalues, the unitary can't do anything. It can add a global phase to that state, but it cannot actually shift populations from that state to any other state. So it's block diagonal. Within a degenerate subspace, the unitary can be as general as you like. So in some sense, you get a form of the unitary that you can reduce to 1, 1, so on and so forth. Then within some block, you have completely general reduced unitary, 1, 1, and so forth. So within degenerate blocks, it can do anything. However, let us look at this form of this thermal state within a degenerate block. So within degenerate subspaces, the thermal state tau of the system and bath is approximately the same, well, not approximately, it scales as the identity operator. And the reason is the following. We know that the thermal state has the property that if I have a population, so the thermal state is diagonal in the energy eigenbasis, clearly, so I can just focus on those diagonal elements, which are the populations. So the population Qn of a thermal state tau is proportional to e to the minus beta En. So it's e to the minus beta En divided by Z. So if En is equal to Em, that implies that Qn is equal to Qm. So within a degenerate subspace, the state of a density of a thermal state looks like it's proportional essentially to the maximally mixed state, which is a state that we know does not change under any unitary operations, which implies therefore that USP on tau SP, USP dagger, is tau SP. And so if you take in as an input a thermal state of the system, you can add whatever thermal state you like of the bath, and you do any energy preserving operation, you're going to get the same thermal state of the input back out again. Okay. And so our free states are thermal states. Okay. Is there any question about this argument? Nope. All right. So the next question we have to consider then, which is the basis for the resource theory, is how do we know that rho can go to sigma? So how do we know that a state rho can go to sigma? So once again, I'm not going to go through the entire proof here, but I'm going to give you the intuition of why the criterion that we have works. So let me tell you what the criterion is. It's called Thermo Majorization. It's sort of a generalization of just majorization. And I'm going to do it only for the case that, because this is the case in which it's clear if rho and sigma are both diagonal in the energy eigenbasis. So if rho and sigma are non-diagonal in the energy eigenbasis, then we have questions on how to deal with the coherence. And this is something that I will deal with altogether when I talk about clocks and the role of energetic coherence in quantum thermodynamics. But for now, we're dealing with diagonal states. So rho and sigma are both diagonal in the energy eigenbasis. So I can write this as a collection of populations. Let's call this, so in this case, even though I usually don't do it, I'm going to call this rho n. And this is the eigenvalue corresponding to En, to the state, the eigenstate En. And so then I have this has a set of population sigma n. And what we do is we take the modified set, we take rho n times e to the plus beta En. So this is some sort of inverse Gibbs factor. And on the other hand, we take sigma n e to the plus beta En. Now this, of course, is going to rescale all of the populations. So you're not going to get vectors that are normalized anymore. So you divide these by an appropriate z, which depends on rho. You divide this by appropriate z, which depends on sigma. And then you check whether these states satisfy majorization question. So if this is the case, then we have that rho can go to sigma via thermal operation. Okay. What is the reason for this happening? So here's the thing. So we have a U system bath that is energy preserving, right? So now if I have, let's imagine that I have a qubit for the system. So the system is a qubit with energies E1, E2, and E3. And these are the states 1 system, 2 system, and 3 system. Okay. If I was to do an energy preserving operation only on the system, I would not be able to do anything because there are different energy eigenvalues. So I cannot move population in between the energy eigenvalues at all. However, the point about thermal operations is that we are allowed to bring in any state that we like, any Hamiltonian that we like from the bath. So of course, the best thing to do is going to be to bring in Hamiltonians that do allow us to shift populations around, which are Hamiltonians that create degeneracies. So what I do now, I've run out of space. Let me start on a new page. So I have these states, E1, E2, E3. And now what I do, this is my system, this is the path. I bring in, so let's call this, I'm going to call the energies here, well, okay, let's call this E0. And then I have 3 states up here. I'm going to, well, actually, I don't need E0. I simply have these 3 states. I call this E0. I call this E0 minus E2 minus E1. And this is at E0 minus E3 minus E1. These are my states 1, 2, and 3 of the system. And I'm going to call these 3, 2, 1 of the bath. So I've picked, what I've done here by constructing this energy level diagram is I've picked a Hamiltonian for the bath. So it can have many states, but these 3 states are definitely present within the bath. And so what we see now is the energy of the state 1, 3, which is equal to E1 plus E0, is also equal to the energy of the state 2, 2, because this is E2 plus E0 minus E2 minus E1. So this is also E0 plus E1, and that's the same as the energy level E31. So what I've done now is I've created a degenerate subspace. In the joint state of the system and bath, we have 3 energy levels whose populations we can move around. And effectively moving populations around these 3 states, once I trace out the bath at the end of the operation, will correspond to moving populations around on the system. Because remember, when we trace out the bath at the end of this, if I have moved population, for example, from 1, 3 to 2, 2, then when I trace out the bath, this is effectively the same as moving population from 1 on the system, so this system and bath, to 2 on the bath. So all of this is to say the following. Even though energy preserving seems like a criterion that will prevent us from moving around populations within the system, because of the fact that thermal operations allow us to append any Hamiltonian we like, we can always create degenerate subspaces between any 2 energy eigenlevels of the system by adding the corresponding gap, the same gap, in fact, in the bath. And this means effectively, and of course you have to add a bit more to close the argument mathematically, but intuitively we see that in fact it is not a constriction for us. We are allowed to move populations between any of the energy eigenvalues, or sorry, energy eigenlevels of the system just by choosing the appropriate Hamiltonians. And remember, thermal operation, I can keep bringing in different systems from the bath and I can keep doing unitaries. All of that corresponds to one thermal operations because I can compose all of the different unitaries and all of the thermal systems that I bring in from the bath under a single unitary operation on the full global state. Right. So all of this is to say that we are allowed to shift populations. Okay. However, and now this is the important part. So imagine now that I've done this, I have managed to bring these three states of the system and a Hamiltonian from the bath such that there is a degenerate subspace which I can move around in and I can do unitaries within. So what is this degenerate subspace? So these are the levels 1, 1, 3, 2, 2, and 3, 1. And so I'm going to look at the populations now within these energy levels. So the population P13, remember I've taken the tensor product of a system state with a bath state. It's going to be the corresponding population on the system, which I'm just going to call P1, times the population on the bath. Now, because we have the Hamiltonian of the bath, we know that the population of the bath is going to be proportional to the Gibbs factor of that energy level. So it's going to be e to the minus beta E naught over Z of the bath. Same way I have that P22 is equal to P2 times e to the minus beta E naught plus E1 minus E2 over Z, and last one is 3,1 is P3 e to the minus beta E naught plus E1 minus E3. Okay, and I'm going to make a nice trick here. What I'm going to do is I'm going to write, so P13, P22, and P31. I'm going to write them as a vector of different numbers. I'm going to take something common out, which is e to the minus beta E naught upon Z, e to the minus beta E1 upon Z. And what do these three values become now? The first one is P1. I've taken E naught out, but because I've taken E1 out, I have to bring it back again. So this is E1. Oh, sorry, there's no need of a repeated Z. What is the second element? I've taken E naught and E1 out. So I'm left with P2 e to the plus beta E2. And as you can see, the same thing happens with 3. I'm left with P3 e to the plus beta E3. Now, what we have done is we have shown that the populations in the degenerate subspace up to normalization look like the populations on the system scaled by the inverse Gibbs constant corresponding to that energy level. And the reason this is important is because once we are working in a degenerate subspace, and we know that an energy preserving unitary is any unitary in that subspace, then we have reduced the problem back to the problem of noisy quantum operations in that subspace, which in turn is the same as noisy classical operations on the eigenvalues in that subspace. So in the end, the operation that we do within degenerate subspaces is the same as just doing a reshuffling of the eigenvalues under doubly stochastic transformation. And we know the criterion for whether this is possible or not. It's if the original set of eigenvalues majorizes the final set of eigenvalues, which is why the vectors that we have to look at are the vectors Pn e to the plus beta En upon a corresponding Z to majorize sigma n e to the plus beta En upon Z. So starting with majorization on the eigenvalues within the degenerate subspace and adding the fact that the eigenvalues in degenerate subspace always have the ratios corresponding to the inverse Gibbs factors with respect to each other. It means that in order to check whether you can take rho to sigma, you have to check whether these numbers, the eigenvalues of rho scaled by the Gibbs constant, can be taken into the eigenvalues of sigma scaled by the corresponding Gibbs constant. And one simple way to consistency check is if rho is equal to tau, which is equal to e to the minus beta, well, you can say sum over e to the minus beta En upon Z, which would imply that rho n is e to the minus beta En. then that would imply that this vector here is just the maximally mixed distribution 1 over ds. N is equal to 1 to d, which is exactly what we would have understood from majorization, because if you start with something whose rescaled values are already the uniform distribution in the degenerate subspace, then that means that any doubly stochastic transformation you can do there will also take you back to the same vector, which means you cannot do anything, which is a consistent way of saying that if you started with thermal state, you would not get anything else. You would end up in the thermal state. Okay, are there any questions on that part? No questions, no comments. All right, let me go on, because I would like to finish a lot about thermo majorization today. So the next thing we're going to do is, oh, sorry, rates of conversion. Okay, so when we talk about rates of conversion, instead of going from rho to sigma, we ask, can we go from n copies of rho to m copies of sigma? So maybe you cannot go from a single copy of rho to a single copy of sigma, but there exists some n and m such that you can go from n copies of rho to m copies of sigma. And now when we want to talk about a rate, we take the asymptotic case. So we say let n and m be larger and larger and larger. And what we take is the limit as, say, n tends to infinity. So for every n, we're going to get some value of m, which gives us the amount of sigmas that we can get from those many of rho. And we take this m upon n, and we call this r, which is the rate of conversion from rho to sigma. Okay. So this is another way of defining a resource theory on multiple copies and asymptotic transformations. So it should be very clear here that if we find the value of r, for example, that's equal to 2, for instance, then this does not imply that we can take one copy of rho and turn it into 2 copies of sigma. It means that as we take more and more copies of rho, the number of copies of sigma that we get will be approximately 2. And in the limit n tends to infinity, that ratio will become exactly 2. Okay, so I do not have so much time to go into the full description of how one would argue what the rate of conversion is, but I can talk about the result, which is that in the case of thermal operations, we get that R of rho going to sigma is in fact equal to this ratio versus tau upon d of sigma given tau. So this, remember, there are 2 ways of seeing this. This is the divergence or the quantum relative entropy. Quantum relative entropy. But another way of saying this is it's also equal to the free energy. So beta times the free energy difference of sigma, free energy difference sigma minus the free energy difference of tau. So the fact that the relative entropy between any state and the thermal state is the free energy difference is very important. So this is now something more sort of more useful than the resource theories we've discussed before, because in every one of the resource theories we discussed before, we ended up with a pre-order, which was the case that some states that we got at the end of the resource theory were not actually comparable. Majorization is a pre-order in the sense that some vectors do not majorize either x majorizing y or y majorizing x. But what we get here in the case of thermal operations, when we look at just the rate of asymptotic conversion and not single shot transformation, is that we do get a total order. The free energy becomes a sort of total ordering of states. because we are given that we can always go from some copies of rho to some copies of sigma if the free energy of one of them is larger than the free energy of the other. And this in turn is something that you can call, well, this is not itself a currency, but from this you can derive the notion of a currency, which is the following. What you can do is, instead of considering that rho tensor n goes to sigma tensor m, what you do is you consider that rho tensor n, you can convert to some, well, yeah, let's call it eta tensor k, and this goes to sigma tensor m, where this is somehow a standard unit of the resource. So for instance, if we were dealing with qubits, then you could take the resource resource, because what you get in this case is that r of rho going to sigma is the same as r of rho going to the standard unit eta divided by r of sigma going to eta. So you have you compare every transformation, you reduce to the transformation of every other resource to the standard unit and back, and this gives you this rate. Then r of rho tends to eta becomes your currency. So I didn't get much time to mention the other very important resource theory in quantum information theory that has nothing to do with thermodynamics, which is the resource theory of LOCC and entanglement, the resource theory of entanglement under local operations in classical communication. But I would like to say a few words on that because this is an example of a resource theory. You have space-like separated systems. So for example, just consider the bipartite case, two space-like separated parties. You're allowed to do any local maps on either side. You're allowed to send classical communication. And then from this construction, you find that the set of free states is any separable state, because you can easily construct any separable state from the combination of local operations in classical communication. The non-free states are any state with entanglement. And in that case, so here you have free states are the separable states. The units of resource you can consider to be Bell states. So then a rate of conversion problem would reduce to a problem of distillation. If I give you n copies of some arbitrary entangled state, which is not free, how many copies of the Bell state can you get from that? And for example, there are some states which are called bound entangled states, from which you know that you can get, no matter how many copies you're given, you cannot distill Bell states out of. So those would be states for whom the rate of conversion would be simply zero, or at least the currency of those states would be zero. The currency of all states that are not bound entangled will be a finite value. And the currency of the Bell states themselves, of course, will be just one. So this is an example of another resource theory. Right, are there any questions? Okay, so if there are no more questions, there is one, okay, so there one final thing to say, and I'm sorry for spilling over time today, and it will take 5 minutes more. So we had thermal operations. And there are a number of different questions we can ask. One is just whether rho can go to sigma. And this gives us thermo-majorization as a criterion. The next thing was to go rho tensored n goes to sigma tensored n times r, and putting in the ratio directly in there. And this gave us the free energy as a monotone. So R is equal to d of rho tau, sorry, upon where tau is the thermostat, sigma tensor tau. The other versions that we can do is we can say, well, what happens if you take rho tensor a catalyst eta, and I want to take it to sigma tensor catalyst eta. So the catalyst has to remain the same at the beginning, at the end. Then what you get is all of the Renyi divergences d alpha of rho tensored gamma minus d of sigma, oh sorry, not gamma, once again, this is tau, the thermostat, sigma versus tau, the alpha must be greater or equal to 0. So the Renyi divergences are a generalization of the, and I don't have the, okay, I don't have the formula at the back of my mind right now. It's very easily Googleable, and I will put it into the lecture notes. But for the Renyi divergences are a family of entropies. If alpha is equal to 1, you get the free energy. If alpha is equal to 0, you get simply the rank of the state. If alpha goes to infinity, you get the maximum value. It's the maximum eigenvalue. And what you get is, under the assumption of catalysis, where the catalyst is returned perfectly, you get that the entire family of Renyi divergences for alpha greater or equal to 0 becomes necessary and sufficient criteria for rho tensor eta going to sigma tensor eta. So this is now another example. And then finally, if you have rho tensor eta goes to sigma tensor eta prime, where this is epsilon close to eta, then we get a subset of Renyi divergences depending on epsilon. So the dimension of the catalyst is important. So you can, for example, say that the trace distance of eta prime minus eta should be less than epsilon over some function of d. And depending on how strong this function of d is, you get a different set of criteria. So with the notion of exact catalysis, you get the entire family of Renyi divergences. If you have, for example, f of d is just d, so that becomes epsilon over d. You have to return the catalyst in a state that is epsilon closed divided by the dimension. Then you end up getting only alpha is equal to 1, which is the free energy difference. And of course, if you have f of d goes even worse than that, so let's say log d, then you get that any transformation is allowed. So when you include catalysts, the assumption on what the catalysts can and cannot do, or how they are supposed to be returned, is very, very important. One of the things to say is that for all values of the catalyst being returned, which are in between d and stronger things, the free energy is always a monotone. It might be the only monotone, or you might add more other sufficient and necessary conditions to it. But the fact that the free energy is a necessary condition is always true regardless. And so the final thing to mention, which is something that you will visit in a tutorial problem, is that if you allow catalysts to be correlated with the systems they act upon, then you get free energy is both necessary and sufficient. So the end result of all of this in the final summary is to say that the resource theories that you get in quantum thermodynamics are very sensitive to the type of operations you allow. One of the things that you always get out of when it comes to asymptotic transformations or transformations with catalysts that are not strictly preserved, but are allowed to either be returned in a reasonable fashion close to the original state or correlated with the systems, which is something that naturally happens, you end up getting free energy as the monotone that defines everything that you can do. But if you have stronger constraints than that, you can get more values. And instead of having a total ordering, which is what you get when there's only the free energy, you can get a pre-order, a partial order with many different conditions that are necessary or sufficient. And with that, I would finish the lecture. If there is any more questions right now, I would answer them.
I have just a very short technical question. The
Yes.
independence of our function f, is that the dimension of the catalyst?
The catalyst. The dimension of the catalyst, yes. The reason for this is because when the dimension of a catalyst increases, you can, for the same amount of trace distance between the catalyst, you can hide a lot of much more entropy and other differences in between them. Because remember, entropy, if I have an arbitrary large catalyst, I can, for vanishing trace distance, have a huge amount of difference in entropy by dividing the difference among many eigenvalues. And this is why you have to add a functional dependence on the dimension to how close the catalyst is returned. Yeah.
Yes, okay, thanks a lot. That makes sense.
Okay, and with that, that concludes the lecture. I will see you all next week or during the office hours.